Okay, everyone, so this is our last lecture, and we have our final exam next week. It'll open on Monday, and it'll close on Friday at midnight, and it'll be online. You just take it like you did the midterm. It's comprehensive, so today I thought I'll just do a review and make sure everyone's comfortable with the material. I've got an example or a study guide here for the final exam. There's two of them on here. So we'll take a look at this one. We'll just run through these questions. If anyone needs any clarification, let me know. So we'll have questions on the RISC ISA, like assembly language and instruction encoding, that kind of stuff. And then there'll be a part on system Verilog. And then we've got the pipeline architecture from your project with some questions specific to that, the microarchitecture rather. And then we covered sequential logic and timing analysis and building blocks. And then finally, I don't have a review section on here for it, but we also covered transistor level logic, CMOS logic. So there'll be a question or two on that. Okay, so here's an example question. It says, consider the following sequence of instructions and their corresponding memory addresses. Assume the code is run on a machine that uses byte address instruction memory, which means that if you look at the addresses are incrementing by 4 instead of by 1, as we have on your CPU. So the byte address. Then there's a question, is the instruction at address 400,000 in hex a pseudo instruction? If so, to what machine instruction does it map? Well, that's a load immediate. There's no machine instruction for load immediate. When you use a load immediate, it's translated to, anyone know? It's translated to an add immediate with register 0. So that's why register 0 always contains the value 0. So you can add an immediate to it, right? Is the instruction address 400,010 a pseudo instruction? That's a branch. Branch. Is there a branch instruction? There's not. There's no branch instruction in RISC. That would map to jump and link instruction, where the link register is register 0. You guys with me? So you remember in MIPS there was a jump instruction that didn't link. There was also a jump and link instruction in MIPS, but in RISC-V there's only a jump and link instruction. They've simplified it, so they've eliminated the jump instruction. I think in ARM there's a branch instruction, which is essentially equivalent to a jump, right? But anyway, yeah, that's a pseudo instruction. And is the instruction at 14 a pseudo instruction? That's a jump register. I don't think so. Unless there's jump and link register. Do we have to use jump and link register for that? Anyone know? Did you guys implement jump register in your CPU? Yeah. You did? Yeah. Jump and link register, right? With register 0? Yeah. Okay. Yeah, so that one's a pseudo instruction. Again, the question is whether or not there's a hardware instruction for these or if they're translated to something else that is a hardware instruction. How many times is the branch at address 8 taken? So this one requires you to be able to understand what's happening in this program. We load 5 into x1, and then we have this loop here where we decrement it each time. So the branch instruction is going to first see x1 as 4, and then 3, 2, 1, and then 0, right? But then it's going to see it as -1. Right? So I think 6 times, right? Do I got that right? See, so you're going to start out at 5. The first time the branch hits, it'll be 4, then 3, 2, 1, 0. That's 5 times, but then it'll actually encounter that branch the 6th time, where x1 will be -1, right? At which point it won't branch, right? It'll fall through, right? Because it's branch as long as x1 is greater than or equal to, but once x1 becomes less than x0, it's not going to branch. But the branch instruction should be executed 6 times, right? Make sense? So the loop is supposed to iterate 5 times, but the branch will be encountered 6 times, right? Based on how it's structured. Okay, what is the fetch sequence for this code, assuming a 1-cycle branch jump stall? Well, the fetch sequence will be, we're going to fetch 0, 4, 8, and then this branch will be taken. But if we have a 1-cycle stall, then even when that branch is taken, we're still going to fetch the instruction at C, right? And then after we fetch C, which will just be a stall instruction, then we're going to go to label 2 and we'll get 14. Right? Does that make sense? Oh, sorry, label 1, which is 4. Sorry, label 1. We go to label 1. Right. Thank you. Make sense? So it'll be 0, 4, 8, C, 4, 8, C, 4, 8, C, 4, 8, C, 4, 8, C. That sequence will happen 5 times. And on the 6th time, we won't take the branch. So we'll fetch C, and then we'll fetch 10, which will be a stall from that jump and link. And then we'll go to 14. Right? And then we'll fetch 18, which is the stall after 14. And then we'll be jumping back to 2, which will be 10. Right? Because the link address from this jowl will be 10. Make sense? Okay. So the point there is that you basically have to follow whether the branches are taken or not, and you also have to remember that you're always going to fetch the instruction right after each, taken branch and jump as a stall. Okay, so how many cycles does the following code require to fully complete execution? Same idea. The same idea here. You're going to execute the first instruction, the second, which will zero out x2, the third, which is checking to see if x2 is 0, which they are, equal. So then we're going to go to skip, but that branch is going to require 2 cycles because of the stall, because you're going to have to fetch the jump and then stall it, right? So that's 1, 2, 3, 4, and then the skip has 1 cycle for loading immediate. So I think that's 5 cycles, right? 5 cycles, right? Assuming 1 instruction per cycle. But remember, you also have to consider the pipeline depth too. So once the pipeline is full, it executes 1 instruction per cycle, right? But in this case, if we're not starting out full, like we're starting from that first load, the load is going to enter the pipeline. There'll be nothing. There'll be instructions behind it, but we're just counting the instructions from beginning to end of the loop. So you have to actually add 2 to this. Does it make sense? Right? So it's 5 cycles plus 2, 7 cycles to finish that on our CPU. So if you ran this on your CPU, it should take 7 cycles to execute that loop, right? So it's basically the number, it's the number of instructions multiplied by the number of cycles per instruction plus the latency or the depth of the pipeline, right? You guys with me? Okay. System Verilog. Identify any problems with the module below. Can't put assigns inside an always, so that's just a syntax error. A and B are 3 bits and C is 4 bits, and so there's a mismatch in bit width between the 2 sides of this assign, right? Is that it? I think that's it. Yeah. I miss anything? I think that's it. To what value will the following system Verilog code set the signal when A is 1011? This is just scrambling the bits of A. So B is going to be 1, 1, 0, 0, right? 1, 1, 0, 0. Any questions on how I got that? Okay, write a system Verilog module named parity. It receives 3 1-bit inputs, A, B, and C. It produces a 1-bit output Y that's true if an odd number of its inputs are true. That's just an XOR, right? You can just do an XOR on that. Right? Odd number? Yeah, XOR, right? So you just assign Y to be A XOR B XOR C. Right? XOR being a caret. Convert the behavior of the following Verilog module into a truth table. So this one is, you've got, so to make a truth table, you have to look at every possible value of the input A. And A is 3 bits, so there's 2 to the 3rd power, 8 possible inputs, right? So A can be, basically 0 through 7, right? And then for each one of those inputs, you have to calculate what Y is, which, so for half of the rows of that truth table, which is basically if A bit 2 is set, meaning that the value of A as a 3-bit value is between 4 and 7, then the output Y is going to be 1, 1. If bit of the remaining 4 values, which would be between 0 and 3, of those, 2 of those have bit 1 set, right? You guys with me? So, if A is A and Y, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So for these inputs, you're going to have Y is going to be 1, 1, right? Now, because it's an if then else, it's prioritized, right? So you're going to consider the other 4 inputs on the else part of this if statement. And so we're looking at these 2 guys would be 0, 1. And then the else would cover the last 2 cases, which is, well, in this case, it could be 0, 0 or 1, 0, 1, right? Make sense? Okay. Okay. Write a system Verilog module named minority. It receives 3 1-bit inputs, A, B, and C. It produces a 1-bit output, Y, that's true if at least 2 of the inputs are false. So you could do this with a case statement. You could do this with an if then else. You could even do it with a ternary assignment. Any questions about that? Seems like everyone's pretty comfortable with the Verilog stuff. Write a self-checking test bench for this module. So the test bench would be, because there's no clock, right? Because this is a combinational logic, right? The design under test is combinational. So you don't need to worry about a clock. So you can just use an initial block to set the inputs and check the corresponding output. You guys with me? The only thing you have to be careful is that after you set the inputs to the design under test, you need a non-trivial delay afterward to check the output. Right? It can be, like using the pound sign, right? Right. Okay, what's the purpose of the sensitivity list and an always statement? It's basically you execute the always statement whenever any of the values specified in the sensitivity list change, right? And if you have pause edge in there, then it only counts if there's a positive edge, right? Rising edge for that signal. Blocking assignments update the assigned values immediately, while non-blocking assignments update the assigned values after other actions associated with the current event have completed. Obviously, this is referring to an always block. How many clock cycles of delay will the code, wait. Is that it's kind of out of context. I don't know what the purpose of that is actually, because this is another question. How many clock cycles of delay will the code impose between input and output? Oh, right, I see why I said that, because of the there is a mixture of blocking and non-blocking in here. Okay, so In this case, this is really bad code. You wouldn't want to write code like this, I don't think. I think this is, but I think it'll still work in model sim. But inval is assigned to A, and then A is assigned to B. Because the first one is a blocking and the second one's a non-blocking, these two guys will activate together on the same edge of the clock, right? So basically, there's only one cycle of delay between inval and B, right? Likewise, there's one cycle of delay between B and D because of the same reason. So in total, there's 2 cycles of delay between inval and D, right? So it'll take 2 cycles before whatever I had as inval gets popped out of the D value. Make sense? Okay, sketch the hardware that the following system Verilog module implies. This is basically just a gate level 211 style, OR gate and AND gate. But there's also a flip-flop on the output of this thing now. So you have to be careful you don't miss that, which I almost did. So what this is doing is creating a flip-flop for Y and for X, right? So you got to put a flip-flop in for, there's 2 flip-flops. So Y and X, right? Okay, and then Y is going to get X or C. So C and then X is going to come around like that. And then X is going to get A and B, A and B, like that. You guys remember this, right, from 211? Yeah. Did you guys use flip-flops in 211? Yeah. Yeah, so basically just 2 flip-flops and 2 gates. And this one is kind of strange because you've got a feedback here, right, between the output of this flip-flop and the input of this next state logic. So this creates like a little state machine, essentially. Right, because you've got, the clock logic and the next state logic. Okay, assume the following Verilog module. This thing just assigns A to not A and B. How many total bits comprise the inputs? 3, 2, A and B. 1 output, C, right? 2 inputs, 2 input bits. How many bits are output bits? There's just 1. And then fill in the missing values for the test vectors. So, if A is 0, not A is 1. Then if B is 0, you're going to AND it with 0, and so C would be 0 for that, right? Make sense? Now, obviously, in this case, I'm showing an exhaustive set of test vectors here. So the second one can be a 1, 1 or a 0, 1. No, it can't be a 0, 1, right? Yeah, it has to be 1, 1, right? Because if it were 0, 1, there'd be no other spot in the table for 1, 1, I guess. Oh, no, there would. No, that would be fine. Yeah, we could do that. Yeah, thank you. Oh, right. Then the C would be wrong. You're right. Thank you. Yeah, that's a good point. Yeah, thank you. Yep. Yeah, so you have to pay attention to the expected out, what the expected out would be. You're right. So if we want to figure out what A is here, yeah, you have to note here that the C is 1, and so A would have to be 0 there. Because if A were 1, then it would be 0 and 1, so the output would be 0. Yeah, thank you. Okay, any questions? Okay, assume the following module, which instantiates the module above. So we have, this is a wrapper. So we have module BBB is wrapping around module AAA, and it's obnoxiously changing the inputs. It's associating C in BBB with A in AAA, and A in BBB with B in AAA. So basically, this is the same table. You just have to pay attention to the scrambled input values. Any questions about that? Okay. describe any problems with the module below. Let's see, we've got 2 always are both driving B, so we can't do that. We'd be double driving B. So that's a problem. And also, these always are always at star, which is another way of saying always underscore comb. And they both imply latches because they don't say what happens to B if the if condition is false, right? So you'd want to put an else on these guys to say what happens to B otherwise if you want to avoid latches there. Describe the process by which a user-entered HDL design is converted from a form may be loaded on FPGA. So what is the process? I don't know if I talked much about this semester, but the Verilog code is synthesized, which is very similar to compiling. We don't call it compiling, though. We'll call it synthesizing, which converts it into a graph representation called a netlist. And then the netlist has nodes in it, which don't necessarily match one-to-one with the nodes on the FPGA. So you have to go through this mapping process where you have to map the nodes. Like, for example, if your FPGA only has lookup tables that have up to 6 inputs, but the netlist has a 7-input lookup table, you have to break the 7-input lookup table into 6-input lookup tables, right? It's called mapping. And then once it's mapped, then you have to place and route. You have to place each of the nodes in the maps netlist onto the hardware, right? And then connect them. Make sense? So synthesis, map, place, and route. And then you have to generate a bitstream file. That's the file that actually configures the FPGA. In this class, they're called SOF files, SOF. Quartus calls them SOF, a serial output file. I think that's what that stands for. But basically, it's just it's the binary file that's shifted bit by bit into the FPGA. It configures everything on the FPGA. All the BRAMs get initialized, all the registers get initialized, all the LUTs get initialized, all the switch boxes that form the connections between the LUTs, they all get set up when you send in the bit stream. Okay, fill in the table for the module below. This is another almost like a test bench, except this one, the difference here is that you've got these clocked elements in there. So in cycle 0, we're going to set A to 0. What's B delay 1, B delay 2, and B? We don't know, right? There's no initial values listed for those, right? So they're unknowns. So they would come up as X's, I think, in Model Sim. They come up as a unknown value, right? We're only going to know what B delay 1 is after 1 cycle. B delay 1 will show up because it'll be the previous value of A. And after 2 cycles, B delay 2 will show up, and it will be the prior value of B delay 1. And after 3 cycles, B will show up, right? So basically, this is a shift register where you're taking the input A, and every cycle it gets shifted down 1 slot. And the order of those slots is it goes to B delay 1, then B delay 2, and then B, right? So it just creates a delay, essentially, right? Okay, write a Verilog module that takes an 8-bit value and produces an 8-bit output value where the upper 4 bits and lower 4 bits are swapped. How would you do that? We use the curly braces. So you just combine curly braces with comma that concatenates, and then I don't know what the values are called. I'll just say A 3 down to 0, comma A 7 down to 4, right? And then you can assign B. Okay. Write a Verilog module called find cycles having the following requirements. So years ago, I didn't give a traditional final exam in this class. I would just give everyone, I would give them like a design problem, and then everyone would come in the lab and I just give you 2 hours to like design it and test it in Verilog, and then submit your code and your simulation result, right, your waveform. And this was similar to the type of thing I might have asked for that. This is a little simpler than those ones, but same idea is that I'd give you a list of requirements. So you've got your inputs and outputs. In this case, those would just go on your module line. And then I'd show you the expected output. And so the idea with this thing is it just sits there and doesn't do anything until you give it a go signal, which is when you assert go for 1 clock cycle. And then after that, it will pulse cycle 7 after 7 cycles and cycle 11 after 11 cycles. So how would you build something like this? Well, this is pretty easy. You would just have to create a counter, right? So the counter would get initialized, you'd start the counter with the go, right? So you'd have to have an internal register that would keep track of whether the thing is counting or not, right? You'd have to have something that you call like running, right? And you'd set running to be, you would initialize running to be 0. And then once you see go, you would turn running on with an always at pause edge clock. You guys with me? Right? So if you saw go, then you'd turn running on. And then at the same time, you would have a counter that would tick up once per cycle whenever running was on, right? And then once the cycle counter got to 11, you'd turn running off automatically, right? So basically you turn it on. So you'd have always underscore FF at pause edge clock begin. Okay, and then you say if go, then running is going to get 1B1. Now the question is, what happens if I say go when it's already running? Like I'm assuming that running is turned off initially, and then I'll turn it on. Well, I didn't tell you what happens in that case, so I'm just going to assume that I'm going to, if it's already running and I assert go, then it's probably going to act goofy. It's not going to give me, like, in other words, I'm assuming that it's invalid to assert go within 11 cycles of the last time you asserted go, right? Does that make sense? Fair to say, right? Okay, so then I'll say if running, then you can have count equals count plus, and then how many bits is the counter? I got to go up to 11, so 4 bits. So 4 apostrophe B1, right? And then if count equals 4 apostrophe D7, then cycle 7 is going to be 1 apostrophe B1. If count equals 4 apostrophe D11, then cycle 11 is going to get 1 apostrophe B1, right? And also if it's 11, I'm going to reset the counter to, I want to reset the counter to 0 because I don't want to put that. So I'll say begin here, and then I'll also set, actually no, I won't even reset the count to 0 for apostrophe D0, and I'll set go to 0. End, sorry, no semicolon. And then also, I need default values for, I'll set cycle 7 is going to get 1 apostrophe B0 by default, and cycle 11 is going to get 1 apostrophe B0 by default, which will be overwritten in this case, right? Make sense? And then end the always. So set default for cycle 7, cycle 11 to 0. If I get a go input, I'll start it running. If I'm running, I increment the counter. Right? If I hit cycle 7, I'll assert that. If I hit cycle 11, I'll assert that. Right? Now the problem is that this is a little weird though, because what's going to end up happening is that if I tell it to go, it's going to set running to 1, but this thing is not going to see that until the next time it activates, right? You guys with me? So the first time I increment count will be the cycle after I turn running on, right? So cycle 0, when the count is 0, that's the first cycle, right? The problem is that according to this, 1, 2, 3, 4, 5, 6, 7. So the counter is actually going to be 0 in this cycle. The cycle after, because it's going to be one, like, so in this cycle, let's see, hold on. This rising edge after go is when I'm going to turn running on, right? So running will be on in this cycle, but the counter will be 0, right? And then the counter will be 1, 2, 3, 4, 5, 6. Right? So actually, this shouldn't be 7. I need to subtract 1. I need to make this 6, because the counter is only going to be 6 on the 7th cycle, because it takes 1 cycle just to turn on the go signal, or the running signal, rather. You guys with me? So this should be 6, and this should actually be 10. So I'll decrement. So I'm going to look for the counter to be 6, which should line up to the 7th cycle after running. Now, another option is I could have just set, I could have initialized the counter to be 1. Also, and of course, there should be a reset here, but I didn't give a reset signal, did I? No, there's no reset here, unfortunately. So there's going to have to be an initial, you'll have to initialize the initial value, then initial begin. We'll have to set count to be 0 and running to be 0. And so we'll have an initial, that initial statement will be implemented by the FPGA being reprogrammed. You guys with me? Normally you'd use a reset signal to reset, but like I said, the problem doesn't state that. Any questions? Okay. Pipeline microarchitecture. We got the 3-stage pipeline. Write a system Verilog snippet to implement the sign extend block. That's pretty trivial. That's just, well, you guys know that, right? You guys all did that, right? So you just replicate the sign bit, with bit replication. The sign bit, by the way, is, in this case, what is the sign bit? The sign bit is, this is sign extending a 12-bit signal, right? So whatever bit 11, so you've got 12 bits coming in here, bit 11's got to be replicated 20 times. Make sense? Okay. Write a system Verilog snippet to implement the block that produces the GPIO out signal. A lot of groups had trouble with this, GPIO out, because they forgot to implement the enable. So when they ran their code on the board, the GPIO out got the value that it should get, but only for 1 clock cycle, and then it got reverted to 0 again, right? Because the enable, it was always enabled. You guys with me? So you need an enable on there. So it's basically always flip-flop, sorry, pause edge, clock, if, what's it called? Where'd it go? GPIO, oh, here it is. GPIO write enable. If GPIO underscore write enable, then GPIO out is equal to what? What is it? Oh, read data 1. Yeah, read data 1. Read data 1 underscore probably EX, right? Yeah. And you don't need a begin and end here because there's only one statement inside the always, and there's only one statement inside the if. So. Write a system varilogs. Okay, got that. In the following table, mark the stage holding each of the instructions listed in the first 4 rows. Okay, so for this one, in cycle 0, we're fetching the load upper immediate. And cycle 1, we're going to be fetching the add I and executing the load upper immediate. And then cycle 2, we're going to be fetching the multiply, executing the add I, and writing back the load upper immediate, right? And so on, right? And then for each of these signals down here, all you have to do is check to see which instruction is in which stage and then fill in the corresponding value for that, right? So for example, when the load upper immediate is being fetched, well, I don't know what any of these signals are supposed to be because none of these relate to the fetch stage, right? So they're all don't knows, don't care. I don't know what, don't. Actually, it should be unknown, right? Unknown value because if this guy is fetched, I don't know what's in the other stages, right? There could be other instructions in there, right? Unless that's the first instruction. So you should put U in there, right? These should all be U's in the first column. And the second column, I'll be executing that LUI. So reg write should be 1, because load upper immediate does write to a register. Reg write WB is, again, an unknown, though, because I don't know who's in write back, right? Make sense? So that's how you figure that out. You just have to match up the signals to what's in each stage. Any questions about that? I've got the solutions to these too, by the way, on Dropbox, if you're interested, if you want to look back. What changes to the design would allow the CPU to execute the made-up instruction, I think it's made up, NVPC, that behaves as shown below? It copies the address of the current instruction into the register file at address RD. Well, but we already do that, don't we? Don't we have an instruction that does that already? The jump and link, right? The jump and link already does that, right? Which PC, though, does it put in the register file? It puts in PC fetch. Okay, well, which PC is this supposed to put? Oh, PCEX. Okay, so this is not the same as jump and link, because jump and link puts the PC fetch in. Now you might say, wait a second, no, we put PCEX in our design. Well, yeah, but so PCEX is PC fetch with a 1 cycle delay for the write back stage, right? So when you guys design your CPU, you should have wired PCEX into the register file for jump and link. However, in this problem, I assume when it says PCEX, we're talking about the PCEX when that instruction is in execute. In other words, the address of that instruction, right? Not the address of the next instruction, the address of the current instruction, right? So this is a little different. I think you would have to actually add another. You'd have to add another register for PCEX. You'd have to delay PCEX 1 cycle and call it PC write back, right? So you would have to add another register for that. You guys with me? Right. So what's the difference? Jump and link is storing the address of the instruction that follows it, right? Whereas this problem is asking you to store the address of the actual instruction itself, right? So there is a slight difference between those, because in this one you'd not want to write back PCEX, you'd want to write back PC write back, right? Which is the address of the instruction that's in the write back stage, which would be this instruction. Does that make sense? Okay. Okay, under what conditions is the stall signal generated? Also, why is the stall needed? Stall is going to be used to have the CPU ignore the instruction that is fetched after a taken branch or a jump. Because by the time you know that you've got a jump instruction or a branch, you've already fetched the next instruction. Make sense? So you can't avoid fetching the instruction that's placed after the branch or jump, so you just stall it. You fetch it and you just don't do anything with it. You don't execute it, okay? What does the PC shown above, does the CPU shown above support the load word instruction? No, there's no memory for load store. There's no data memory. Write a sequence of 2 RISC instructions that would trigger the register file bypass. Basically, any instruction that writes a value that's read by its immediate successor. So if you have a add that writes to read x2 and then another add that reads from x2, that when this guy is in write back, this guy will be in execute. And so the problem is that this guy won't actually write back until he's out of the write back stage, right? So in other words, this instruction is in the process of writing x2 while this guy is in the process of reading x2. So you have to trigger the bypass, right? You can't, because otherwise if you didn't have the bypass, this second instruction would get the old version of x2, not the new one. You guys with me? Alternatively, you could just not tell the compiler not to do that. You could program the compiler not to actually generate code like this. And if it has to generate code like this, then it could just put a no-op in between. Problem solved, right? But it's be slower code. So the bypass is really kind of a performance enhancement, right? A performance improvement. Or performance, it's a feature designed to improve performance as compared to not having it. What would happen if the register file lacked write bypassing? Well, then, like I said, you'd have to have you couldn't have 2 adjacent instructions with a dependency. Consider the RISC-V design below. Is it possible to add support for the add with write logical shift? Oh yeah. So this instruction is actually on ARM processors, believe it or not. ARM processors support this thing called a flexible second operand, where you can actually do certain things to the second operand, like shift it before you feed it into the ALU. It's pretty cool. It's useful for things like fixed point, for instance. Can we support this? Not with the hardware we've got, right? Because you need to add some hardware like to do the shift. You might say we have hardware to do the shift, the ALU. Well, yeah, but the ALU also has to add. This instruction has to shift and add. We have to do 2 things. We only have 1 ALU, so you have to add hardware for this. Make sense? Like a second ALU. Using the delays in the table below, what's the minimum clock cycle time for the processor design above? Ooh, okay. So this is something I always wanted to add to this course, which is once you've designed your CPU, how fast can you clock it? Because we're only clocking them at 50 megahertz, which is pitiful. I think our CPUs could run faster. But I don't know how much faster. I never actually tried to make them run faster. I would guess that you might be able to run those things on this FPGA, 300 megahertz maybe, right? But the question is, what's the limitation, right? Well, it depends on these propagation delays. So if these are our propagation delays, then what's the critical path of our CPU? Well, first of all, it's got to be the execute stage, right? So in the execute stage, we are reading memory. No, that happens in fetch. Execute, we've already read the memory. So register clock to Q, I think we still have to pay for the 10 picoseconds. So I think we'd start with 10 picoseconds. And then we have we have the instruction memory. So I think that's going to be 10 picoseconds, right? But then we're going to go into the register file, right? But then we also go into the control unit, right? And then from the register file, we go into the ALU. And then from the ALU, we go back to the register file. But there's a mux in between the ALU and the register file, right? Because we have multiple things we can write back, right? For example, CSSR and LUI, right? So there's a mux here, right? So we have 10 picoseconds propagation delay. Register file read is 100, register file setup is 25. But let's do register file read 110. So that's 110 picoseconds there. There's a mux here too, right? On the ALU. Multiplexer 30 picoseconds. So we have 30 picoseconds here, and then the ALU is 100 picoseconds. And then we have another 30 picoseconds here, and then the register file setup time is 25. We have to get the result we've got to get there 25 picoseconds early for the setup time, right? Make sense? And the control unit, that's 100 picoseconds. But see, that's happening in parallel with all this, right? So that control unit controls that mux and that mux. But, you know, that path is much, well, you got to go through, yeah, that path is shorter there because you got to go through 110 picoseconds for the register file, right? So the critical path would be this top one. Make sense? You guys with me? So what's the total? 10 plus 110 plus 30 plus 100 plus 30 plus 25. So that's 120, 150, 250, 280, 305, 305 picoseconds. I just made these numbers up, by the way, but they're probably reasonable. So 305 picoseconds. Actually, they're probably not reasonable because 305 picoseconds would be like 3 gigahertz. I don't think the FPGA is going to run that fast. But you know what? On an FPGA, in practice, most of the delay is not in these logic, it's in the wires. The wiring delay is longer generally than the logic delay. And I didn't even give you any wiring delay here. Wires on an FPGA are really long because the FPGA is very sparse compared to an ASIC, right? Because it's more spread out because the LUTs are larger than the 6 input LUTs on an FPGA are bigger than a 6 input gate on a custom chip, right? A 6 input gate is only 12 transistors, right? But a 6 input LUT is, a 6 input LUT is storing what? 64 bits, and each bit is 6 transistors, right? So remember, logic, CMOS logic, if you have a 6 input gate on CMOS, right, would be 12 transistors, right? But remember, we learned a LUT, which is a RAM, right? A RAM would be 2 to the 6 power bits, 64 bits, times, remember there's 6 transistors per bit in a RAM, in an SRAM. That's what LUTs are, SRAMs, right? Right, so this is going to be 64 times 6 versus 12. So 402? 402 transistors for a 6 LUT, 12 transistors for a 6-input gate in a fabricated chip, an application-specific integrated circuit, right? So the FPGA has about 30 times less density in terms of logic than a chip that you send out in fab, right? And so the result of that is wires that are like 30 times longer, which have a lot more delay than the wires, because the wires have less, the capacitance and the resistance of the wire scales up with its length, right? So if the wires are longer, that means more capacitance and resistance, which means more time to charge it up and discharge it, right? Which means that the wire delay is longer, right? So that's what's going on here. That's why FPGAs are, but I still think this CPU would probably run at 200-300 megahertz if we really pushed it. If we started to learn how to read those timing report and be able to tune our design, maybe make the pipeline deeper if we needed to. Anyway, what would happen if the reg select EX was stuck at 0? Then you'd only be able to write whatever that corresponding mux input is, right? The load up or immediate. You'd only be able to do load up or immediate. Of the instructions, add, subtract, branch if equal, CSRW, and then I give the CSRW parameters there. That's the reading the switches, right? For which is the reg write signal not asserted? Branch if equal, right? Branch if equal doesn't write the register file, right? You guys know that, right? Okay. What data path changes are needed to add support for the branch on less than instruction? Wait, don't we have that? I thought we had that instruction. We have that, right? Yeah, we have that. Yeah, I don't know, nothing. How many ports do each of the memories of the CPU have? How many ports? Well, there's two memories on the CPU. There's the instruction memory that has 1 port because we read 1 instruction per cycle. And there's the register file that has 3 ports because we can support up to 2 reads and 1 write per cycle, right? All right, another CPU. Yeah, same idea. This one, you just figure out what the control signals are. What instruction is fetched in cycle 6? What? Cycle 6. Fetch, fetch, fetch. Oh, cycle 3, sorry. Did it say 6? Oh, there's one for 6 too. Okay, so in cycle 3, we fetch none, right? Same as in cycle 6. But why do we have fetch in cycle 4? Because we have the branch, that's why. Oh, I'm sorry, I forgot, we have the branch, right? So that we have a branch here that this branch is taken. And so we fetch the first instruction, second, third, and after the third, we fetch in cycle 3, we're going to be fetching the fall through for the branch, whatever comes after the branch, right? That's the stalled instruction. And then in cycle 4, we're going to be fetching the add. Cycle 5, we're going to fetch the second add. In cycle 6, we're going to fetch the branch, right? Make sense? So is there another way we can express this? So let's do it this way. We have add I, branch if equal, right? Okay, now the branch if equal is going to go up. So remember that this -2 is relative to itself, right? So that means 1, 2, right? That's not the same as MIPS. In MIPS, -2 would have been the add I, the second add I, right? But in RISC-V, that offset is relative to the branch instruction itself, right? So we're going to fetch the first add I. But right after the branch, we're going to have a stall, actually, right? And then we're going to, I'm going to just call this 1 and 2. Then we're going to fetch add I 1 again, and then add I 2, and then the branch if equal, and then the stall, right? So the cycle that we fetch these guys in is going to be 0, 1, 2, 3, 4, 5, 6, 7, right? So the question says, who are we fetching in cycle 3? That's a stall. And who are we fetching in cycle 6? That's a branch of equal, the second branch of equal. Make sense? Okay. Make sense? Because there's a branch. I was confused initially because I forgot there was a branch in there. Okay. Oh, by the way, is this taken both times? I'm assuming it's taken both times. We're going to put 2 in register X2, so that'll be decremented once, and then decremented twice. Oh, so actually the second branch is not taken. So it's going to be whatever's after the branch, fall through. You guys with me? So there was another curveball in there, right? Because you're going to initialize register X2 with 2, and you're going to decrement it once, so it'll be 1 the first time I hit this branch. Oh, but wait a minute, I'm going to reinitialize it though, right? So never mind. So I keep going to reset it to 2, decrement it to 1, reset it to 2, decrement it to 1, reset it to 2. So actually, sorry, so that would be a stall. It is going to be taken. That's an infinite loop. It's an infinite loop, right? Because that branch, every time that branch is taken, it's going to reset register X2 back to 2, right? So, okay, so suppose the reg cell WB was stuck at 3, what would be the impact? Reg cell stuck at 3, what's 3? Register select. Is it, do I have it? Oh yeah, right here. PCEX. Right, so it's going to only be able to write the program counter value to the register file. All right, sequential logic. What's the difference between combinational and sequential logic? Combinational is a function of its inputs only, whereas sequential logic has memory, so it also includes information about past inputs, potentially, right? Difference between D-latch and D-flip-flop. D-latch uses a level-sensitive clock, and D-flip-flop is an edge-sensitive clock. Consider the circuit below, write the next state logic and output logic in Boolean algebra. Well, this is easy. Basically, Q0, the next state logic for Q0 is Q0 prime, and it's just going to be A ANDed with Q0 or Q1, right? So you just have to trace the wires back, translate the... so you guys already know how to do this from 211. The only thing that's new between now and when you took 211 is this notion of next state logic. The next state logic is the input to the flip-flop, right? And the current state logic is the output of the flip-flop. Okay? You should have learned that in 211, but I don't know why they don't cover that. Can this circuit operate at 2 gigahertz? Well, we got some propagation delays here. No. Oh yeah, we have all the stuff here to figure this out. So, all right. So the delay is going to be the T PCQ. PCQ. You guys remember what that is? That's the time it takes to actually change the output of the flip-flop. The flip-flop's propagation delay, right? And then we have to add the delays of the logic, the critical path delay. What's the critical path? Probably these two guys, OR gate and AND gate. So that's going to be 30 picoseconds plus 85 picoseconds. 30 plus 80 plus setup time, because we got to set this guy up. So setup time is 100 picoseconds. That seems extreme. Okay, plus skew 10 picoseconds. Okay, now all of this has to be less than 500 picoseconds, right? Is it less than or equal? I think it's less than or equal, right? Less than or equal. Okay. So TPCQ is, what was that? 50, yep, 50. So this is 50, so this is 80, 160, 260, 270. Yeah. Seems comfortably fits in there, right? Make sense? Okay, what about, that's the setup time. What about the hold time? The hold time is the short path. So it's the contamination delay of the flip-flop, which is TCCQ plus the short path. Short path. What is the short path? It's the probably just the AND gate, right? Yeah, AND gate by itself. Contamination delay of the AND gate is 25 picoseconds. And that has to be greater than the hold time. The hold time is 20 picoseconds. And plus the skew. Right? What's the skew? 10. Right? And what's this guy? 5. Okay, so basically 30 picoseconds has to be greater than 30. Uh-oh. Well, that's an issue. Right, so this would violate the hold time. But it's, it's pretty close. Make sense? You guys with me? That's an easy one to fix, though. You can just add more delay. Okay, next state function, again, that's similar. And then we have this elevator example. Okay, so this one, sketch the state transition diagram for the finite state machine described by the system Verilog code. So this guy has a type def with 4 states, so there's 4 states. Clock logic is pretty standard, it just says that the start state is S0. And then the next state logic is shown in the next state logic. So we've got 1, 2, 3, 4. What are they called again? S0. Okay, yeah, S0. How creative. S0, S1, S2, S3. And looks like A and B are our inputs, which are just 2 bits each. Okay, so if A, wait a minute, really? What, they're 2 bits? Why? Okay. Okay, if A XOR B, next state, if I'm in S0, right, if my current state is S0, and A XOR B, then I go to X1, S1. So A XOR B, what does that mean if they're 2 bits? That means that they are, if they're both the same, so A doesn't equal B. If A doesn't equal B, if A equals B, then the XOR will give you all zeros, right? Make sense? Otherwise, the next state is S0, which means that's a wraparound, right? And if you're in S1, A and B, we're going to S2, A and B. Yeah, I guess that's if A equals B, right? Or no, yeah, no, but what happens if just 1 bit? As long as they're not both different. Yeah, I think that's a typo. I think those were supposed to be the same width. I think they were supposed to be 1 bit each. Because it's kind of confusing if they're 2 bits. So I'm going to assume they're 1 bit. Right? So I'm going to say they both have to be 1 to go take that transition. Right? Otherwise, you go back to S0. That's your default transition. And then S2 is going to, if A or B, then you go to S3. So as long as A or B, so as long as one of them is 1, right? So A or B, right? And then otherwise you go back to S0. And then if you're in S3, if A or B, you stay in S3. Otherwise, you go back to S0. Make sense? Okay. And then the output logic is, the output is what? The output is Y. So Y is going to be 1 here. And Y is going to be 1 in S2. And then Y will be 0 here, and Y will be 0 here. Okay, that's the output logic, is just this one assign statement at the end. Okay, any questions? All right, so we have another timing. I'm going to skip that. Another timing question. Glitch. Could the circuit potentially glitch if a single value is changed? Yes. Right? This circuit could glitch if you jump from this Carnot map group to that Carnot map group. So for instance, if A and B are both 1 and C and D are 0, 1, and you changed A, if you changed A, that might cause a glitch. And you could fix it by adding another grouping that covers. Actually, you just want to cover these two. Right, you wouldn't want to include any zeros. All right, another timing question. Digital building blocks. Give a Boolean expression for the carry-in input for column 3 of the following type of adders. Use multiple equations to construct the expression. Oof. Okay, ripple carry adder. So, so the ripple carry is going to get carry in 3 is going to be the carry out on 2, right? The carry out on 2 is going to be A2 and B2, or A2 and carry in 2, right? Or B2 carry in 2, right? And then carry into is going to be the carry out on 1. Carry out on 1 is going to be pretty much the same thing as this, right? A1, B1, or A1 carry in 1, or B1 carry in 1, right? Carry in 1 is going to be carry out 0 equals, and then pretty much the same thing again, right? You guys with me? Right? Make sense? So these would all have to be nested. Carry look ahead adder, on the other hand, would be, what is it? Carry in 3 is going to be the generate from 2, or the propagate on 2 and the generate on, propagate 2 and the generate on 1, right? Make sense? But we're not done, because you can also have propagate on 2, propagate on 1, generate on 0, right? Or you can have the propagate on 2, propagate on 1, propagate on 0, and the carry in 0. Make sense? You guys remember that? So the propagate just means that it's going to propagate its carry. The generate means it's going to generate a carry regardless of what happened on earlier columns to the right. Make sense? Okay. Design a schematic for a 32-bit comparator that takes inputs A and B, sets as output Z if A is greater than B or 0 otherwise. Yeah, so pretty much you obviously have to subtract and check to see if the result is negative. And how many gate delays are needed for a shifter that performs an arithmetic right shift by 4? Ooh, for a 32-bit input A. How many gate delays are needed for a shifter that performs an arithmetic right shift by 4? Any ideas? Well, that was that mux-based design that we looked at, right? So basically, but actually, the mux-based design assumed a variable for the shift amount, right? But this is using a constant shift amount, right? So how would we build a constant shift amount? No gates, right? A constant shift amount is all that's doing is just reassigning the bit indexes, right? So pretty much if you're shifting right, you're just chopping off the rightmost 5 bits and then putting zeros in to the left side, right? So that requires nothing. That's free. So a variable shifter is really, the irony is that a variable shifter is very expensive because you have to be able to essentially build a mux where the number of inputs to the mux is the number of bits that you're shifting, right? Right? That's a barrel shifter. But a fixed shifter is free. Okay, fill in the Boolean expressions below, and I'm just about out of time, aren't I? Okay, so there's only one question left. It involves the prefix adder. So if you have any questions about that, let me know. Any other questions about anything? So I didn't review obviously didn't review the prefix adder. I also didn't get to the CMOS logic. So make sure you check that out too. That was the last 3 lectures I gave was on CMOS logic.